Hello, everyone. Welcome back now to the finale, so to say. And we have a panel discussion as well as a Q&A session. And I hope we can all collectively make it very stimulating. I think the idea is to look forward, and Spenta will kind of lead us through it, and so will the panelists. So over to you, Spenta.
Thanks, Rajesh. We've had a very exciting week here in which we have heard talks which have covered almost all aspects of the applications of quantum mechanics to the natural world. So before I proceed with my opening remarks, I'd like to introduce to you the panel that is here. The first one over here is Dr. Barbara Terhal from Delft University. Then is Pedram Roushan from Google Research, California, USA. Then Professor Philip Kim from Harvard University, Physics Department, and Arindam Ghosh from Indian Institute of Science, Physics Department, and Juan Maldacena from the Institute for Advanced Studies at Princeton in USA. Okay. I will also be calling upon members of the audience who have given talks or anyone else to answer a few questions, because several of the questions has been addressed to specific people in the audience. So I will just do that also, and I hope it's okay with you. And I'll also invite, originally we had Rana Adhikari from Caltech to be with us, but as you know, he could not make it here. However, there are two young students, one student and one postdoc actually, one from Nodita, Srinath Manikandam, who works on the observation of gravitons. And also I just met in the afternoon Shruti Malaikal from Caltech LIGO, who will make a few remarks on the work they are doing at Caltech. Okay? All right. So it is fair to say that present experimental evidence in all the fields of the natural sciences, as practiced on planet Earth, show no inconsistency or deviations from the laws and principles of quantum mechanics. This includes atomic and molecular phenomena up to length scales of 100th of an angstrom, that is approximately 10 to the minus 10 meters, and nuclear and elementary particle phenomena up to distance scales of 10 to the 19 meters, which is 1 part in 10,000 of the size of the proton. Furthermore, there is solid experimental verification of the violation of Bell's inequalities, which results from a fundamental property of quantum mechanics, non-classical property of quantum mechanics, namely quantum entanglement. And among others, I am referring here to the experiments of Alan Aspey, performed in around 1981-82, and then, of course, many other tests of the failure of Bell's inequalities that were performed at Delft University, the University of Vienna, and the National Institute of Standards of the USA. So in some sense, quantum mechanics seems to be in a very good shape as a fundamental theory of the real world. And precisely because of that, it has had a major social impact. I mean, cannot imagine our lives without what quantum mechanics is doing for us. And I think it'll be nice to, at some point, list in the public media the impact of quantum mechanics on our social life. Okay, well, then back to physics. The last point I would like to make is about the possibility that quantum mechanics and our ideas of space-time may need a modification at distances of the order of the Planck length, which is approximately 10 to the minus 35 meters, or equivalently time scales which are of the order of 10 to the minus 44 seconds. Our present investigations to try to understand phenomena at those scales, which is called string theory, assumes that we keep quantum mechanics intact, and we may perhaps change our ideas of space-time. at those length scales. Now, is it possible that the future generations that meet here to celebrate at ICTS quantum mechanics at 200 would be discussing the invention of new laws and framework of which quantum mechanics is a limiting case, just like when we dial the Planck's constant to zero, we smoothly go from, well, not smoothly, but go from quantum mechanics to classical mechanics. And this point has also been raised in one of the questions by Senthil. Okay, with these few remarks, I'd like to invite Barbara to tell us about her thoughts.
Yes. Well, as you've heard in my talk, also I'm concerned with quantum technology. And maybe a question is quantum technology also going to lead to answering questions of physics? I mean, in some sense, building a computer is building a closed system. You could say that having a classical computer doesn't teach us anything about the laws, about the laws of physics. And well, I can say a few things about how hard it is to build a quantum computer. But it's also a bit of a question, are we going to build a closed system, which is like a classical computer, just something that we can do simulations of, or we can factor large numbers? Or are we going to have a model that also interacts with the outside world, so more of an open system? And in some sense, you know, the current development of classical computing you see with neural networks and so on, in some sense, these become, you know, intelligent, open beings that at least can absorb, interact with information, not so much with the physical world. So maybe quantum computing somewhere is an opportunity to build devices that better interact with the physical world as we human beings do. I don't know. So I mean, if you learn about quantum computing, it's more about building a device that can factor large numbers, a closed system, and this is largely an engineering challenge. I'm a theorist, so I'm not going to be very instrumental in this challenge. It's hard to assess how this is going to go, but maybe one point I'd like to make. So a few years back, there was an estimate that to factor a large number, which would be relevant today, would take 8 hours and 20 million noisy qubits, noisy superconducting qubits. So this looks very daunting, given that we have a chip now of 100 superconducting qubits. So it's clear that scalability of devices, superconducting qubits, but also trapped ion qubits and neutral atoms, that's going to be the frontier. It's going to be the frontier in terms of, you know, power consumption, speed, modularity, interconnects, and this has also been alluded to in some of the talks. Yes. So the other question is indeed, will we use quantum computers in some sense as detectors? And again, maybe in the Google experiment, there was also some events that were noticed once every hour. The qubits were a lot more noisy and wasn't fully understood why that was the case. And that's kind of tantalizing that actually by making very high precision devices, we can actually make maybe better measurements. But then it has to be an open system. And about theory, it's a big open question. And I think Peter Zoller also alerted to that. What we can do with a quantum computer, you know, beyond what we know right now. So what problems we can solve? How can it help us do physics or chemistry? And it's hard to assess this because we don't have computers, so we can't run heuristic algorithms and just try things out. We have only noisy devices which have limited depth in terms of the computation they can do. Okay, so these are a few thoughts maybe to start off with.
I do quantum mechanics in an industrial setting. The mission of our team, which is very close to my heart too, is to make a quantum computer and enable computations that cannot be done otherwise. I want to say, in the light of recent progress that we had, I'm becoming actually quite optimistic that the hardware challenges can be, in fact, overcome. and particularly in error correction, when the destination is to a good degree determines what logical qubit to make, and one logical qubit and then two logical qubit and whatnot is very much more determined where we are going. The hardware challenges by putting good teams of engineering can be overcome, and I think it's realistic to assume that we will have bigger processors in the near future. What actually is surprising maybe to me is we don't know what to do with these processors. But let me just, as I was mentioning during my talk, the focus of my work is in having very good qubits without making logical qubits, having very low error qubits, and try to do physics or some interesting application with them. But the fact that we don't have a very, what we call a killer app, a very clear destination to do, is very perplexing to me. So the biggest open question is, I give you a few hundred qubits, there are 10 to the minus 5 error rates and whatnot. What to do besides these non-equilibrium dynamics problems that we do and entertain our own community? What is a killer app to do? And the fact that there's not that clear applications ahead of us is very strange to me, and to me this is the biggest challenge, and it's very strange to me. I would not think this way 5-10 years ago, that the hardware would be so well ahead of the theory work. And if I've just said something I read somewhere, probably is all wrong, but there are about 30 algorithms that are accepted or so by the community for, I think these are fault-tolerant algorithms. And then 5 of them, they show a proper scaling, but 5 of them are more interesting, and they're all coming before the year 2000. So many decades and no clear algorithms that we are all excited about is actually, I think, is the biggest challenge. But to be fair, there are hardware challenges too, and I can say material science and the coherence of the superconducting qubits is, of course, has been the biggest challenge, because you're working with a solid state setting and you have to overcome defects, and well, they have the fancy name of TLS. These are really the biggest bottleneck. But managing heat load and wiring and packaging, I think I'm very optimistic these can be, to a good degree, work out. But if I want to make a prediction to be a bit provocative, maybe, I think I would predict that in the next few years, in the near future, we will see some better usage of these processors. I don't know exactly where. So I'm actually, at the end, I'm optimistic someone come up with some very interesting thing, and this processor would be actually have a very good usage even before fault tolerance kicks in. It's just my feeling.
So my research field is probably representing the quantum material research. So quantum matter, quantum material research. I think this is also a very exciting time. A lot of progress has been made, but also a lot of the task is remaining to be solved. My view that one of the biggest problem in this field is how to understand this very strongly correlate many-body system. I think Subir gave excellent talks. Shankar and Cynthia also gave this touch upon this the important issues there. There are only a few handful of this kind of well understood kind of model problems. We know that how to understand the emergent phenomena appears in this very strongly correlated many-body problems in quantum matter. Yet experimentally observed this emergent phenomena is actually growing over the time. And how we can understand that, I think one of the biggest problem is a 40-year-old problem of high temperature superconductor issues, how we understand that mechanisms and how we understand, kind of improve that even. That is one of the herald problems. But there are more and more of those kind of examples arises. And what is the frame of this, the view that understand that those kind of many-body problems. I think that's kind of biggest the pie out there, I view. A little bit closer goal, I would say, related, but not necessarily directly kind of the equal, is try to find out the way to realize the topological superconductivity. I think this is, especially in the lower dimension, 2D and 1D topological superconductors, has a direct connections with fault-tolerant quantum information processing, which actually ties back to quantum computing arguments that arises in previous panel members. So that is kind of important issues. There are many proposals out there, and the many experimentalists also work on to realize this topological superconductivity in various platforms. I think that's kind of in probably near future goal that one can achieve. Another part that the purely material side point of view is there a way that we can engineer this material really in the atomic scale to build up the materials by designing and engineer the material? I think that's also kind of very exciting field. There has been quite a progress. I think the semiconductor heterostructure is a good example, using MBE that one can construct these materials by designing from the theory to predictions that kind of closed loop can be made. Recent progress of the Wadia engineering, Twistronics is another example that reasonable capability of the experimental engineering is possible to realize different functionality of materials. I think these type of these things, good example, but eventually we want to kind of push that into the limits that whether we can just do the really atomic scale of the engineering to build up the materials that by designing. And of course, the tied with our understanding, enhanced understanding of this the emergent phenomena in the strongly correlated system, potentially this is a way that we can just kind of open up the route to get into the, say, room temperature superconductor, for example, and such a kind of fantastic applications that can really change our lives using the quantum mechanics. I think that's kind of something I want to kind of share.
Thank you, Spenta. Thank you, Philip. So I think my area of research is very close to Philip's. So what he did is essentially say the overall importance of material physics and material research that would lead to a strong impact on the quantum research in coming decades, probably require, leading to new technologies, and technologies will feed back into more research. It's a feedback loop. So I don't want to go in that direction because that has already been expressed by all the esteemed panel members. I'm, in addition to being a quantum researcher myself, working on two-dimensional systems and looking at various fundamental aspects, I also wear another hat where I kind of look at some of the management aspects of quantum in India. So my experience over the last year and a half or so, let me sort of share a couple of directions on that. So what I find is, without any doubt, as an expert in quantum domain working for more than decades, one thing is for certain, that we still do not have the final say on almost any aspects of quantum, that what would be the final platform on which whether the computer will be made or whether a sensor will be made, and so communication protocols and so on and so forth. So clearly there is a significant amount of research that has to go in. But it's not about just the research, it's about the research management, which means that if there is a research output in some part of the quantum, it's a material aspects or a new algorithm, how can that be connected to other parts of quantum to make a whole process become more efficient? What I find is that today, at least in the country that I come from, and I'm not sure it's not true for other countries as well, is how we create a network of expertise or people who can translate one aspect of quantum to the other. And that helps the entire community to grow. If there is a beautiful new sapphire substrate or a tantalum superconductor, which can make a better qubit with lower coherence, that material science people must be able to connect with people who are making superconducting qubits to implement that and put there in their structure. Now, quantum management, in my opinion, is going to become one of the major areas where people will have to put investments. and necessary courses and education must be done covering the entire spectrum to create people who can connect the dots. That said, actually, the second point that I wanted to talk about is about quantum education. This is particularly true for, if you look at history, in the mid-70s and 80s, when the classical computers were coming up, a very counterintuitive phenomenon occurred, which today is called productivity paradox. The reason behind this productivity paradox is there are a lot of engineers who had to be trained about how a classical computer has to work. And as a result, you needed to move a large number of workforce into getting into learning how the classical algorithms are implemented, how the hardware is created. And today we probably have a similar situation in terms of quantum computing. If tomorrow quantum computing has to become as large as classical computing today, there needs to be a very large section of engineers that needs to be trained. Do we have that infrastructure of the system that engineers can be trained at the large scale without affecting the economy? The productivity paradox means the economy actually went down by several percent during 70s and 80s, and after 90s it started picking up again when the computing systems were becoming more and more standardized. So we need to ask ourselves the question, where do we start teaching quantum mechanics today? Do we start teaching quantum mechanics in the form of the quantum technology today? Do we start from schools, high school level, early college level, where education must start so that the people come up with that expertise in the next, within the next 5 years to a decade or so? My last point will actually be, again, an experience that we face at the government level, and it's becoming more and more clear that it's going to be here to stay, and that's called quantum protectionism. I know today Google is making fantastic computers, putting them on the cloud, and we are all using them. As time progresses, and you can see bigger and bigger embargo on quantum products, and thank you. Tomorrow, will there be a governmental restriction for who and what purpose can access Google's quantum space? How we overcome the protectionism in order to make quantum research and development accessible to everybody? Is there a process that needs to be created for that? The same thing, and the last point here, is the IP. We are getting into an era where smaller and smaller IPs, in particular the quantum space, is becoming important. Do we require an international understanding between different governments, as well as research institutions and researchers, to create IPs that are respected? And as quantum becomes more and more strategic, there is a chance that IPs will not be respected. What kind of structure we need to create for protectionism of quantum intellectual properties?
Okay, so I talked about the quantum theory of gravity. I think in this area, the biggest open question is how to describe cosmological situations. In particular, how to describe the very first instances of the Big Bang, or maybe a more practical way to ask the question is what happened before inflation. So we now have the theory of inflation that predicts many good things. We don't know whether it's completely correct or not, but we suspect it is correct. But we don't really have a theory for how we got there. So what happened before? In fact, the theory of inflation is connected, could be preceded by a theory of so-called eternal inflation, where the universe is expanding and then decaying into different bubbles where the laws of physics are different, and we can have a tunneling between expanding universes with various laws of physics. And that, in the far future, would produce a universe which may be uniform at the scales in terms of the laws of physics at the scales we see, but at very long distance scales, we could have regions with different laws of physics. And one question is how to make predictions in this type of landscape or in this type of situation. And we think that theories such as string theory predict, indicate that such a structure would exist, and we really have no idea how to, from first principles, how to get reasonable probabilities. And so just to give you an idea of the type of problems I'm talking about, so you probably all know about the cosmological constant problem. So where you have a factor of 10 to the 120, right? That's the smallness of the cosmological constant. Now it could be that there are many vacua and there are more than 10 to the 120, and we just happen to live in the one that we live, maybe perhaps for anthropic reasons. So that's the cosmological constant problem. Now, when people start thinking about probabilities in this landscape, they get answers where the predictions seem to be wrong by a factor of the exponential of 10 to the 120. So different ways of doing the computation differ by such a factor. So it's really a bit of it's a wild west of an area of quantum gravity, and as the Wild West, I think it's a land of opportunity. It's the frontier. It's what we hope is the type of problem we hope we'll understand in the next few years. And let me, how much time did I run my 5 minutes already? Or? No, okay. Let me say this in a slightly different way that may be illuminating. So as we go back in time, the universe was smaller. As we look at the universe at bigger scales, we are seeing a picture or have some information about how the universe was at earlier times. So for example, when we look at the cosmic microwave background fluctuations that we discussed, the wavelengths appearing in those fluctuations tell us about, the characteristics of those fluctuations tell us about what was happening at the universe at the relatively early stages of inflation. And the longest the wavelength we look at, we are looking at earlier and earlier times in that inflationary period. And now, and the current theory explains that very well. But if you imagine looking at extremely long distances, of course, we have quantities in our universe that are constant, such as coupling constants and many parameters that are really constant in our universe, which perhaps could be different depending on the vacuum of the whole laws of natures that we have. And we don't have any way of making predictions for those. So we think that perhaps the full quantum gravity theory will give us probabilities for different values of the coupling constants. And we don't have a practical way to, we don't have even the framework in which to make these predictions. So, and those are properties of the universe at longer scales. And this type of eternal inflation idea say that at extremely long scales, we can have big variations, big fluctuations in the laws of physics, going to different values of the coupling, different types of gauge groups, and so on. Okay, and I hope that recently there was a lot of progress in the field of black holes, understanding the role of different topologies, and we hope that some of these lessons will be useful for this problem, and many people are starting to get into thinking again about this type of problems. Okay.
Now, what I plan to do is that, we had requested people send in questions. There are lots of them. So I have selected a certain subset, and I will sort of read out the question and invite either the people from the panel or experts from the audience, because some of the questions are specifically asked of some of our speakers. So I know that Vedika has to leave at 3:30, so I just take her question first. So there's a high school student by the name of Jitu Varghese. I don't know whether he's here or not. So Professor Vedika Khemani, is quantum computing still struggling to make a serious progress due to engineering difficulties like AI had in the 1980s. Can I interpret quantum computing as a prediction of many worlds, since David Deutsch in 1982 mentions it in his paper? Also, does Deutsch curves allow us to solve NP-complete problems very good? And does it imply time travel to exist? He's a school student, so. Why don't people from past come to us, etc., etc.? And I also saw Dennis Hessabis saying AI could eat quantum computing, that is simulating quantum systems. How many qubit machine we have latestly developed? I just read it out verbatimly. So could you respond to some parts of it?
Can I just ask Pedram to respond? Because he's the actual person building the quantum hardware.
Okay, sure.
And the many worlds is Google's latest blog posts, courtesy of that. So I think he should own it.
Let me dissect it and see who picks up which part. There is serious progress. Can I interpret quantum computing as prediction of many worlds? I don't know. Okay. Well, our progress should not be interpreted that way. Deutsch curves allows us to solve no NP-complete problems very good, and does it imply time travel do exist? Who's one? Time travel?
Let me comment. No one wants to comment on the other things. I'll comment at least on the time travel. Time travel does exist. We're traveling to the future. Okay, trivial comment. But we can't travel really to the past, and that's a basic feature of special relativity. And we think that that's part of the laws of nature. So we don't think that's possible.
There is something associated with Demis Hassabis, which I know the discussion behind the scenes, so I can comment on that. Indeed, Demis Hassabis has been saying that quantum computing, AI could eat quantum computing. Yes, that's something along this line, maybe not exact word using eating, but I think that's not quite correct because the computations we do it take advantage of the exponentially large Hilbert space, and at the end of the day, it all translates to how much memory you have in your classical computer. And this actually is a fundamental limit that our beyond classical experiment shows that, although classical computations can catch up, but at the end of the day, one is a scaling polynomial, another is exponential. And that's, there is no way that there would be a competition, but then at the end of the day, quantum computers in the tasks that require exponential large Hilbert space is going to be superior.
Okay, I think, thank you. You see, there was an age spectrum in the questions asked. There are very young students from school, college, and I felt I think we should address some of them. And there are, of course, questions from very senior and well-known researchers also, which I will come to later on. So there are approximately 14 questions here, I think, and yes, we have taken one now. So the following question is from Nihal Rishi from Ayuka, that is the Inter-University Center for Astronomy and Astrophysics in Pune, in India. And the question is the following. That's on page 1. Do we have a definition for observer in physics? Does it require a mind? Without going into mind-body problem, or is it necessary, a sub-question, to answer where we stand on consciousness now? Given a 100-year development, do we have any understanding of it, or is it wrong to include the notion of observer in the first place? So I think the panel may want to comment on the notion of observer. Please, Barbara.
Yeah, I can say something about it. The way I see it is that there's some devices that we have, for example, measurement devices as we have them in the lab, that you could call observers. And you could even run this device with an AI completely running autonomously without any human being involved. It's just that to understand its functioning, you just need classical physics. And you could call that the idea of an observer. And it could react based on what it's seeing to the world. It could, perform some other action, like do another measurement or control a qubit. So I don't think so. Of course, the advent of AI has also posed the question: what is it to have a mind, right? I don't think having a mind is actually very special. I think we're just animals, and animals are very interesting. Nature is very interesting as an engineering thing that has happened. And anyhow, but that is, I'm not sure. So I think there is room for observers, but that's not necessarily coupled to human beings. It's just coupled to what we describe classically versus for which we need a quantum description. And classical physics is part of the quantum domain, but in some settings, we don't need quantum physics to describe the functioning of the system. So that would be my answer, and probably people disagree.
Okay, so but I think the question about quantum mechanics that with the observer being part of the system or from outside, I think is a very deep one. I mean, at least I don't understand these things completely. So I thought that using this question, one can somehow raise this particular question. Whether in the universe, we are part of the universe. So we are part of this whole system, but we describe quantum mechanics as if we are a separate system. So some comments on that will be appreciated, actually.
Maybe I can start a little bit, although this is not necessarily my my expertise. But I think that one thing happens over the past 100 years in the quantum mechanics is that I remember that when I was in college, when I learned the first time quantum mechanics, always this measurement is always kind of mysterious. The wave function collapse and the measurement, take as axiom, then sometimes it's quite non-trivial and counterintuitive, and a lot of mysteries that kind of surrounded around this that measurement issues. In some sense, in probably past half centuries or so, that a lot of experimental tools got evolved, and then that while that indeed first time the quantum mechanics was developed, that measurement system is classical system, and interaction between the quantum and classical system is not well defined and well characterized, and that's why this axiom is needed. But now I think some of the measurement process becomes more kind of controllable and understandable. So I think that one of the talk that given in this symposium is also that you can see that small measurement the probe amplitude versus large, and you see that how the wave function collapse is happening. I think those kind of beautiful results. So now it can be characterized, quantified. So I think in some sense, the initial idea that our observer is needed and subjective part and those kind of things, a little bit of now solved the problem in my opinion, and many things can be just kind of get into the quantifiable, the experimental, the test can be done. And that is one of the feat that we have in past 100 years, in my opinion.
Yes. Juan, you want to say something?
Of course, when we think at the universe as a whole, the observer should be included. And as we all know, the standard description of quantum mechanics, the observer is outside. So I think there have been people who thought about how the quantum observer, how the description of an isolated system with the observer inside works, and how the experiences of this observer should emerge. But I feel, well, at least I personally don't understand those prescriptions well enough, and I think it is an interesting question.
Thank you. I think Peter Zoller, in his talk, tried to explain to us actually precisely this question: what does it mean to make a measurement and collapse into a certain state? Peter, you want to say something or add to this?
Thank you. I would say that we have made a lot of progress in sort of understanding how measurement work in actual devices. For example, in quantum optics, based on quantum noise, We developed, for example, continuous measurement theories that gave rise to quantum jumps and all of these things that on some level, in the context of devices, answer these things. But to address it on the fundamental level, like you're talking about over here, I think we are not. And it sort of reminds me a little bit also this question being discussed here when we talk about, for example, time, the meaning of time, and at the end of the day, it's really that you define a quantum system that has, some finger that's moving, some pointer, and you look at the correlation of the system that you would like to observe with the one which you call the clock and things like this. So I would say that on this level, somehow, quantum physics, the observer versus the other one, has correlation sort of enters. But I'm not sure that I have a deep answer here. Thank you.
Okay, let's move on. Sorry.
Can I? Spenta. Yeah, I just wanted to make one comment. As Peter was saying, there is a whole set of experiments that have now been possible because of the attosecond pulse generation, femtosecond pulse generation, where for example, measurements to tell what is the time taken for an electron to tunnel out of a metal in a photoelectric effect. How to, for example, when there is a excitation of a molecule or a atom from one wave function to another wave function, can we watch it as a function of time, this transformation from the one wave function to other wave function? Can we picturize a wave function and take a picture of the electron orbitals in the molecule? So there are lot of time-dependent quantum mechanics experiments that have shown a lot of some of these possibilities and measurements that relate to some of these questions.
Vijay, you want to say something?
Yeah, so I thought I will add my thoughts to the way I understand this problem and why some aspect of it are still not solved. Of course, there's a growing community of people who think that this is not necessarily an important question because it has no practical implication on anything you do, right? The issue is with the measurement is that you are creating an interaction between what we call a quantum object versus something classical which we can actually read, right? And I think Philip was referring to the examples I gave in my talk, where the classical object is the quantum object is the superconducting qubit, and maybe semi-classical object is a bunch of photons. And the way to think about it is that you're really creating a sort of an EPR pair kind of thing, where one part of the pair is the quantum object, and the other part is this slightly semi-classical object. And in any general measurement chain, this second pair becomes progressively classical in the sense of the size of the system. Now, a very careful experiment could control, and this may be possible already in some platforms, that intermediate situation where the second object is not too classical, you can retain the quantum coherence there, because essentially that's what is happening, right? I can define my photonic state as a coherent state with two different phases. So I have an EPR pair with the qubit in the ground state multiplied by the coherent state corresponding to the phase shift of the ground state, plus the qubit in the excited state multiplied by the photons in the coherent state with the other phase shift. And this photon is now separated from the qubit and it's traveling, and you can, in the experiments, of course, these distances are very small, but you can imagine a thought experiment where you have a semi-infinite superconducting transmission line where these photons are traveling freely for arbitrary large distance, and this is exactly now an EPR pair, where one partner is somewhat classical, bigger, larger number of photons. The challenge in general is how long can you maintain coherence in that photon channel, like in this classical object. And this is where practicality comes in, is that as the size of that system becomes bigger and bigger, it decoheres easily. And that's where you start bringing in the idea of decoherence, that now this is going to couple to an environment where the number of degrees of freedoms are very large, and you can no longer keep track of this problem, and hence you say, okay, that superposition of two photonic states collapses into one of them, and that, because of the entanglement, collapses your original system. In these experiments, we can observe what is happening on one of them. So the example I showed you, that the system actually continuously evolves from a superposition state to one of the eigenstates corresponding to the measurement operator. But the issue which I think this thing is called the von Neumann chain. Like, you keep bringing in more and more entities into the picture. Initially, there may be two, but then there could be larger as you keep getting entangled further and further. And then the question is, where do you draw the line? And I think this also has a name of, it's called, I think, the Heisenberg cut. And that's where the complication arises. We have to still choose an arbitrary point to make that cut and say, okay, now I'm going to call this classical. It collapses into one of these two options, and then that causes a measurement in the original thing. So this part is still not resolved, but I think a lot of us think that this is maybe not really an important question, or maybe just it's not a question that makes sense, just like many other things in quantum mechanics. I think David wants to say something.
Yes, David. It's coming.
I just wanted to relate what I recalled reading in a lecture of Sidney Coleman. He was describing that he himself gave much thought to this and was very troubled by it. And at one point, maybe after some sleepless night, he came to the conclusion that nothing could make a measurement except himself, that he alone could collapse wave functions. And apparently he told this to Yakir Aharonov, and his reply was, and did your father collapse wave functions before you?
Okay.
That's all.
Right. Thank you. Okay, I think let's move on.
I think Michael wants to.
Okay. Oh.
Just a sort of historical remark. One aspect of classicalization is, of course, decoherence, the uncontrolled external influences that obscure interference effects. This was really discovered by Thomas Young in 1801. He was bitterly criticized for his demonstration that of interference, two-slit, etc., and claiming that this demonstrated the wave nature of light, by a reviewer who said, if you really are saying that interference is the evidence for the wave nature of light, why don't we see it all the time? Now, Thomas Young did some of his experiments with candle flames, so he had to be very careful in describing the conditions under which you can see interference and you mostly don't. He realized that interference was suppressed by influences he could not control. This was formalized slightly a little later by Fresnel, and then Rayleigh understood it. So it really goes back a long way. Now, the modern aspect of this, which I learned from Wojciech Zurek, is that the sensitivity to external influences increases exquisitely rapidly as you approach classicality. And the example I gave him, actually, which he wrote about, was that if you imagine the chaotic rotation of the satellite Hyperion as being a quantum rotator. Hyperion is a potato-shaped rock about the size of New York City, which rotates chaotically, tumbles chaotically, with a chaos time of about 30 days. If you consider that as a quantum rotator, it has about 60 Plancks in its angular momentum. You can calculate how long it should be, if it were isolated, for this classicality to be replaced by a quantum recognition and suppression of chaos because of the discrete nature of this spectrum with this 10 to the 60 Plancks. Well, you can do the calculation. It's about 40 years. Now, it's nonsense. You don't observe for 40 years and then see Hyperion behaving differently. And the reason is it's not isolated. And you can calculate how long it would take to decohere the state of Hyperion if you have just a single uncontrolled photon from the sun whose re-emission we see Hyperion by. And it's about 10 to the minus 50 of a second. very, very quick. So there's, the density matrix becomes diagonal and whatever. You can do quite simple calculations. So as you approach classicality, systems get bigger and heavier and whatever, they become more and more exquisitely vulnerable to decoherence. So that's one, not the only, that's one aspect of classicalization. But it goes back to Thomas Young, and it's worth recognizing that.
Thank you. Shankar?
Yeah, when I taught quantum mechanics long time ago, this is the question I faced the most of the time, even from graduate students. And actually, the issue here is decoherence, right? We have a system, we have an environment, and decoherence connects them. But in almost all cases, actually all cases I know, that the question really is how sharp is this distinction between system and environment. Question in nutshell is that. In all experimental situations, Philip does experiments, Arindam does experiment, Pedram, you do experiments. This distinction is obvious. There is no ambiguity about this distinction. When you do experiments, you never have to worry what is system or is environment. So my challenge to the students always was, bring me an actual experiment. Don't talk in hypotheticals. Bring me an actual experiment. I can clearly tell you what is the system, what is the observer. Until that happens, I'm not going to worry about it. Then I spoke to Tony Leggett, who, as you know, doesn't believe in decoherence. So he told me, what happens if you include the environment as part of the system? I said, well, then I'm going to go outside and there'll be environment. And you keep on expanding, then you have the universe. And that's, of course, Wheeler is to talk about the wave function of the universe. But to some extent, I think this is hypothetical because our experimental precision, partly because the reason Professor Berry just mentioned, has not reached that stage. I do not know of any experiment where you cannot distinguish system and environment very, very sharply. And as long as that happens, there is no problem. Then it's like, how many angels you can fit on the edge of a pin. Someday this question may come, but I think that's far in the future. Physics is not there yet.
Thank you. I think I want to now do the following. As I mentioned in the beginning that Rana Adhikari is not here, unfortunately. So I would now like to invite Srinath Manikandam from Nordita, who is a collaborator of Frank Wilczek, and they are thinking about observing gravitons just to make a brief statement about the type of work you're doing. You can give the mic to him.
Hi, thanks. So I'm Srinath. I am working at Nordita, Stockholm, the group of Frank Wilczek. So in two recent works, we have shown that it is possible to detect individual single gravitons, and this is a problem that was widely thought impossible. As you know, gravitons are expected to be the quanta of gravitation, and in the linearized theory, in the low energy regime, we expect that they populate gravitational waves. But the reason why people like Weinberg and Dyson thought this might be impossible is because they were essentially thinking about wrong detectors and possibly wrong sources to get the job done. Weinberg was considering individual atoms as detectors which had very small absorption or emission rates for gravitons. And then Dyson was also, for example, looking at if LIGO can detect individual gravitons based on strain sensitivity, and that strain sensitivity that one would require at LIGO would be several orders, 10 raised to 36 orders of magnitude better than what they currently have. And LIGO is also not a good detector to see quantized energy exchanges because they measure position, and one needs to make an observation of an observable that has discreteness. And this is where we showed that if you look at massive acoustic bar resonators, which are essentially huge 15 kilogram aluminum or beryllium cylinders, in the LIGO band frequencies, that means somewhere between 100 or kilohertz and so on, they can get their acoustic modes, they get a collective enhancement as opposed to individual atoms that can increase the possibility of stimulated processes, basically seeing a quantum jump stimulated by classical gravitational waves in the LIGO band frequency and amplitude windows. And so this is a bit like the photoelectric effect. So it could tell that if you see quantum jumps happening on the matter side, stimulated by gravitational waves, that would one can conclude that it suggests that the gravity must be it is a clue that the gravitational field must be quantized. But then one can so the first until now what I told was work with Igor Pikowski, Germain Tober, and Thomas Beetle. And then we had a second recent follow-up work which asked the question whether we can further say anything about whether a semi-classical description where you treat gravity classically but matter quantum could also, it could in principle explain the same effect, because the exchange of graviton is of the order of h bar omega, and for a classical gravitational wave in the LIGO band, which contains 10 raised to 36 gravitons, this is a small negligible change. So then one could say that we could apply Sudarshan's optical equivalence to say that I can replace the classical gravitational wave in a coherent state with a coherent state amplitude to do my calculations. However, what we find is that there are instances where we can discriminate with the same detector whether the gravitational wave is in a coherent state or a highly squeezed vacuum state or a thermal state. And what we need to do is that we look at the lowest order clique probabilities, that is seeing no quantum jumps, 1 quantum jump, and 2 quantum jumps, and make a ratio. And this ratio can probe the second order coherence function for the optical field, which means if the gravitational wave is in a coherent state, I'll get a number which is 1. If it is in a thermal state, I'll get a number 2. And if it is in a highly squeezed vacuum state, I get a number that is equal to 3. So in principle, so this was work with Professor Frank Wilczek, that we can see we can see individual gravitons absorbed from gravitational waves, and LIGO can, for example, tell if there was a classical gravitational wave chirping through our resonant detector at this time. And the second point is that there are certain classes of states. For example, non-linearities are expected to be very relevant in the last stages of processes like black hole merger events that produce these gravitational waves. And they would have measurable signatures that would allow us to tell whether it is a semi-classical description for gravity that is valid at our detector, or if it is something beyond semi-classical detection. Thank you.
Thank you. Thank you. Now, may I invite Shruti Malaikal? She's a student of Rana Adhikari, to say a few words about this subject. Sorry. Oh, just 1 minute.
Yeah, I had a very interesting discussion on this very interesting proposal, but I recall at the end you said, correct me if I'm wrong, in the end you need a 40 kilogram bar to be cooled to its 0 phonon ground state for this to work.
We need something like 15 kilogram beryllium detector. Yeah, 15 kilogram beryllium detector that is cooled to pick one of the acoustic modes, say the fundamental mode, and cool it to its quantum ground state. And let's say we can do this with parametric feedback or laser, some technique. Then one can maintain this at 1 millikelvin, so that the stimulated absorption rate of gravitons will be higher than the thermal excitation rate for a good quality factor acoustic resonator.
Thank you. Shruti?
Hi, I'm Shruti. I'm a PhD student under Radha Adhikari. And I mean, on representing the work that we do in our group, most of our work is on maintenance and upgrades of the LIGO instrument currently. And the work I personally am a part of is to use parametric processes such as the nonlinearity in nonlinear optic materials, and also optomechanical nonlinearity to use these parametric processes to provide quantum enhancement in the quantum sensing that of classical signals that gravitational wave detectors and other similar quantum sensors do. But I was also asked to speak a little bit about something that other members of my group do, which is detect the noise that would arise from a quantized theory of gravity. So there's an experiment mainly headed by Lee McCullough called GQuest, and this is an experiment which is also an interferometric experiment that could detect fluctuations that arise because of the quantization of gravity. And this is based on the theory of Catherine Dirac and Eric Verlinde. And unlike some other theories of quantum gravity, there are very few free parameters in this, so it's actually possible to eliminate this much easily. This is sort of related to the holometer experiment in Fermilab, which also put a lower bound on an upper bound on the possible quantum the level of quantum gravity noise that you could measure. And from an experimental point of view, this experiment called GQuest uses, instead of homodyne detection and other the more classical types of photo detection that we use in LIGO, this experiment uses single photon detection, and so is actually, in a sense, free from quantum noise, and it would be able to detect the quantum gravity noise much better.
Thank you. Okay, so now let's continue with the questions that have come in. There's a question from Abhishek Dhar. Is there a rigorous and general derivation of classical mechanics from quantum mechanics? I believe that the Ehrenfest derivation is an attempt, but not really complete. Who would like to take this question? The panel. Yes, question number 9. Juan? Okay, Michael.
I can say something.
Sure.
I mean, maybe it's a question of...
Afterwards, Michael, just 1 minute. Yeah, please.
Yeah, maybe, I think maybe this question and many questions we ask are maybe sometimes the wrong questions. Now, I'm not saying that this is particularly the wrong questions, but we can say, should there be a very general derivation without specifying, what physics are we talking about? Quantum electrodynamics? Are we talking about standard model? What setting? And as indeed Michael Berry alluded to, what our universe tells us is that there are many degrees of freedom that are fairly highly interacting. It's hard to isolate a system. That is a fact that we experience. You can ask why that's the case, right? Well, that's maybe a given thing. But that has certain consequences that may be hard to capture just in one theorem, right? It's circumstantial evidence that we use and that we observe that at macroscopic scales the world appears classical. But I hear also that there's no law that says that has to be the case, and that's exactly what we're trying to show also with quantum technology, that with enough control, we can actually stop this classical world from, sort of emerging, right? Because if you say, Vijay talked about the measurement chain, where does it start to become classical? There's no specific point that we can point to, of course. We can just look at the microscopics. Okay, you go from millikelvin to 4 Kelvin to room temperature, you amplify the signal. What happens in all these processes in detail? That's the only thing you can do. And you can say, oh, instead of adding thermal noise, I add a very controlled signal, a lot of photon in a very particular state. And then you'd have less decoherence, of course. Then it's more quantum, right? So maybe that's my answer, that why should we expect there is a derivation of classical mechanics from quantum mechanics? Maybe the person who asked the question has a specific goal in mind, of course.
I'll come to him in a minute. Michael?
So the answer to the question, which was, has classical mechanics been derived from quantum mechanics? That was the question. I
Yes.
understood it. The answer is yes, but it isn't simple. And it depends on how you ask the question. I'm not disagreeing at all with what was just said, but I put it this way. There are easy parts of the question. You know, Dirac told us that when you think of h bar going to zero, and I'm speaking all the time as h bar dimensionless, that's very important, you know, commutators become Poisson brackets. That's an easy thing. At the level of equations and formalism, there are simple things you can say. But at the level of solutions to the formalism, then you have to reckon with the fact that the limit is singular. It's mathematically singular. When philosophers talk about emergence, and this is one example, classical emergence from quantum, they use words and they miss this feature that the limits involved, certainly in physics, are always mathematically singular. And I'll give you the simplest possible example. Consider two beams of particles in opposite directions. Well, intensity 1 plus 1 equals 2. That's classically. Quantum mechanically, you have two plane waves. The intensity is 4 times cos squared x, distance, times momentum over Planck's constant. Now, when Planck's constant goes to 0, this becomes an infinitely rapidly oscillating function, cosine of something on h bar. The kind of function that when we learned mathematics at elementary level, we were told, well, this is pathological, it never ever occurs in science. Well, here you have it. So what's the classical limit there? It's, strictly speaking, if you have no decoherence, it's a pathologically oscillating function that takes all values between 0 and 4. Well, of course, in reality, and actually also in principle, there will come an oscillation so fast that you can't resolve it. And then, of course, the average of cos squared is a half, and that's how you get 2. So when I give public lectures, I say that 1 plus 1 equals 2 is, of course, a classical theorem in pure mathematics. But in applied mathematics, you have to be careful to know whether it actually applies or not. And it doesn't apply to two beams in quantum mechanics or beams of light. There is supposed to be, and I've never found it, a paper by Lord Rayleigh, why are two candles twice as bright as one? Which, of course, is exactly this point. So there, you can't avoid bringing in the notion of decoherence in understanding quantumly or optically why 1 plus 1 equals 2. This is a more general point. Applied mathematics is different from pure mathematics. You have to ask whether the mathematics applies. You know, two people get together and produce a child. 1 plus 1 equals 3. Two droplets of water come down the windshield of your car and coalesce. 1 plus 1 equals 1. Mathematics doesn't always apply. You have to be careful. So the classical limit of solutions of the formalism, and I just gave you the simplest possible case, inevitably involve pathology and singularities. We more or less understand many of them, and the random matrix theory of eigenvalues that I talked about is one example, but there are many. So the answer is yes, it's a singular limit. May I just take a moment and give you an everyday example of a singular limit?
Sure.
Imagine you bite into an apple and you see a maggot. You are not happy. If you bite into an apple and see half a maggot, you're of course even more unhappy because it means you've eaten half the maggot. If you find a quarter of a maggot, you're even more unhappy. Take the limit. Smaller and smaller fractions of a maggot, you're more and more unhappy. So you might think that if you encounter no maggot at all, you'll be infinitely unhappy. Of course you won't. It's a singular limit. Not so unfamiliar.
Thank you very much. So Abhishek, are you satisfied with these answers or do you have a comment?
Okay, I mean, it's not completely clear to me. I mean, like what I'm really, what I would really like to see is, I mean, I take a particle in, let's say, some potential, and it has a mean position and mean momentum, which, so is there some limit? I mean, h bar. So it's not clear to me what dimensionless limit one has to take. so that I can see that these expectation values follow exactly Newton's equations. And till what time scale? I mean, there should be some time scale because there's wave packet. Let's say I take a wave packet. I mean, it will spread, of course, right? And so the mean position might satisfy Newton's equation for some time, but it spreads, and then it doesn't make sense to talk of a classical particle. So, yeah, I just want to understand the precise limits where the classical, till when the classical description is validated. I think I had a discussion with Shankar. I don't know if he wants to say something.
Yeah. I think we...
Yeah, we had a long discussion. That's why. I mean, he thought Ehrenfest equation solves the problem. I feel it doesn't. Yeah, yeah. H bar going to zero limit is singular, as Professor Berry already said, and as Barbara said. So it depends on the context. I'm just going to stop there.
Okay, thanks. Rajesh, till 4 o'clock, or what is the time allocated? Around 4 o'clock, right? Okay, that means So now Deepak Dhar is asking, would one of the experts comment on the present status of the many worlds interpretation of the measurement problem? Who would like to take this question in the panel or in the audience?
I think we already talked about the measurement problem a bit, so maybe.
Please,
So I don't have anything to add actually, because I feel like we already discussed the measurement problem, and
yes,
many people said, "Well, I don't really know, but there are sometimes practical answers that there are things that come out of the lab that make us understand measurement better." Of course, they may not bear on the many worlds interpretation, but it's an interpretation, right? It's not supposed to tell us what we measure. Yeah.
Deepak, you have some response? Just Mike, Deepak.
I was sort of trying to ask the question as a student of quantum mechanics. This question always comes up, and I think a clear answer that the many worlds interpretation is not particularly useful in any context is not said anywhere in the textbooks I read or wherever. And I thought maybe some clear statement of that sort will be useful for the general students.
Agreed. I agree.
Would the people in the panel
agree.
like to make a vote and say something about this? No? It will just help the students.
I think the book by David Deutsch is an excellent book that I would recommend students to read. But on the side, I think it's an interpretation, and it's something that it's nice to discuss. And I think he has very lucid ideas about this, which prompted him to think about, a quantum Turing machine and so on.
Sure. I
mean, enough people have analyzed this thing that any of the interpretations doesn't have any practical consequence on what you do in an experiment. So my answer has been choose the one which makes you sleep at night, and that's the one which works, because it doesn't really, at least so far, we have not found that a particular interpretation helps you with anything practical you're doing in any realistic setting. I mean, it goes back to Shankar's comment that give me an experiment where this creates a problem, and then you can explore it in more detail. And you can extend the same idea to this problem of why we don't see macroscopic superpositions. I mean, I often wonder what experimental condition or Hamiltonian where you can evolve a Schrodinger equation which results in a human being ending up in a superposition of separated from 1 meter. It doesn't happen. So the atoms and electrons are happy in their superposition state in their microscopic world, but it has no consequence for these kind of questions. So I think the interpretation question is still very, very open, but it's, again, for a lot of us, it's maybe not the right question.
Hopefully it's an experimental question ultimately, it's,
I think that it has not been formulated as an experimental question as well. What is it you're going to check? I mean, the new thing, again, I thought it was actually going to be a question to Pedram about, that Google's unfortunate comment in the blog post that the quantum computing result gives credence to the idea that multiple universes exist. I mean, so the logic behind that argument is saying that, because this is so amazingly powerful, it must be happening in multiple universes. If that makes you feel happy, great. But it has no, it doesn't prove anything one way or the other.
Okay, thank you. I will go now. The next question is. Sorry.
Oh, Bhaskar, I'm so sorry.
No.
I'm so sorry.
Since there was reference to Daesh book and so on, there's a beautiful little article by Phil Anderson in one of his books about many world interpretation as applied to electron interference in quantum dots. He talks about, it's a very thought-provoking article I referred to. I don't remember the contents, but there is an article by Phil Anderson on many world interpretation as applied to quantum dot electron interference.
Okay, thank you. Next question is from Senthil. Is quantum mechanics the end of the road? Is it even mathematically possible to embed it into a larger structure so that quantum mechanics may be an approximation in some limit? I think it's a very interesting question. So anybody on the panel would like to address? Juan?
Well, probably. We don't have a nice example, but it might be that if we dig deeper into the theory of quantum gravity, where we have to deal with the observer and so on, it might be that quantum mechanics only exists when you can separate the observer from the observed. Some kind of emergent phenomenon that arises in this kind of context.
Yes, Senthil, would like to. Mike.
Yeah, with gravity, all kinds of things can happen, I guess. Black hole interior, maybe quantum mechanics modified or something. But suppose I restrict myself to situations without gravity. The kinds of experiments that lots of the people in the panel would do. And, I don't know whether it's meaningful to ask a question about our world. So I want to ask a mathematical physics question. So in situations without gravity, is there a mathematically consistent way of extending quantum mechanics into embedding it into some other structure? It's a question for mathematicians and or maybe for mathematical physicists. So I wonder whether anybody, in some non-trivial way, not just adding nonlinear terms or something, has anyone in the 100 years thought about this question and made any progress?
I think it's a very interesting question because I think, if I remember, there are some theorems that if you take the deformation of the Poisson brackets, the only thing that you will arrive at is the star product or the quantum commutator. So perhaps you're asking a question like that do we have some other? But I think this will be definitely decided by new experiments, which will give rise to some new parameter, maybe 100 years later. I don't know, just like H bar. Is that something like that you have in mind? I mean,
saying even without experiment, purely as a mathematical exercise, is this possible, or mathematics doesn't allow this to happen?
Okay.
Right. So then, then we are happily stuck with quantum mechanics.
Barbara?
Yeah, just want to make comment. I know people in the quantum foundations, they work on non-signaling theory. So there's a generalizations of quantum mechanics that say they allow no signaling. So, information has to still go with the speed of light or some finite speed. And for example, if you can have a violation of Bell inequalities in quantum mechanics, but you could have a stronger violation that still would not allow signaling. And this is something that Popescu and Werlich defined. It's called the Popescu-Werlich non-local box. And you can imagine a world with those boxes, and you could consider the consequences of having those boxes. But to me, these look indeed very much like interesting constructions. Mathematically, they're very far, maybe from varying Poisson brackets or something. But and there's no experimental evidence, and that is, I think, is the limiting thing here.
Okay, thanks, Michael. You have.
I think it's inconceivable or barely conceivable that quantum mechanics will not one day be falsified and shown to be part of something bigger. We're a species of limited intelligence, newly evolved. We've been doing science for merely a few hundred years. It's ridiculous to think that somehow we've reached to the bottom basic level of the universe with our quantum physics. We're a bit more intelligent than dogs, but a dog can't understand quantum mechanics. They smell better than we do, and they have ways of navigating the world, but they can't conceptualize in the way that we can. But we're limited too. There's a problem, though. Going back 100 years, the development of quantum mechanics was informed by many, many experiments. I've recently read a biography of Heisenberg. Almost every week there was a new experiment that he factored into his developing ideas of matrix mechanics. We don't have that at the moment. As often been mentioned, quantum mechanics is too good, but it's unimaginable that we as our limited species, and by the way, science has worked as well as it has because we do it collectively and we understand more than we can individually, and that's very important. But it's inconceivable that we've reached the limit of the universe. Instead, we may have reached the limit of our own understanding, and who knows what humanity might or might not achieve in the future. But we must be limited. So the answer is surely quantum mechanics isn't the answer. There'll be something encompassing, and as mentioned, people are groping towards it. There are different formulations, and good luck to them. But it will be good to have some experimental guidance.
Shankar, then David.
I'm going to expand on what Michael said, but I wrote a whole New Scientist article on it. I find it very depressing to think that 10,000 years from now, a panel sitting there will use quantum mechanics to talk about interpreting the universe. Obviously, there'll be something new. And the first part of Senthil's question, there is nothing logical or mathematical about the existence of H bar. It followed from experiments. So saying mathematically quantum mechanics is consistent, it must follow, I don't even understand these statements. I mean, if those experiments did not happen, H bar would not be here, there'll be no quantum mechanics. I'm missing the point of it, okay?
David?
But I wanted to, bring back a historical event where quantum mechanics was falsified, and maybe it will be an example of what could happen in the future again. That we have a quote perfect quantum mechanical solution of the hydrogen atom. You have a Schrödinger equation, you solve it, it all works. Oh, except it doesn't. There's a Lamb shift, and maybe we should just tweak the quantum mechanics a little bit, but that's not how it works. That quantum mechanics fails. Now, okay, it just means there's a field. There are fields that also are, essential degrees of freedom in describing the hydrogen atom, the quantum electrodynamic fields. And so I guess that's not the kind of violation that the question was asking about, perhaps, because you say, oh no, well, of course, that's also quantum mechanics, just the quantum mechanics of quantum fields. But it was sort of a near miss, you might say, that it does say that any particular limited theory that we make, that we say is quantum mechanics may well fail, and did in that case fail.
Surat?
Yeah, so Senthil, I wanted to just add to Juan's comment about the importance of gravity. I think the relevance of gravity in understanding the limits of quantum mechanics is not that in gravity anything goes or maybe crazy things happen, but rather that gravity forces you to think of a cosmological setup where we are not separate from the system. The usual von Neumann theory of measurement says you modify the Hamiltonian by adding a term that couples the apparatus and the system. But of course, in the universe, we can't modify the Hamiltonian. We are in one state. And so whatever measurement is happening through some autonomous evolution where you have some state and it's just happening. And maybe in a cosmological context, it's not always possible to neatly separate a notion of an observer away from what the observer observes. And so that's the only sense in which gravity is important. So if we just think of a setup where measurement happens in this autonomous way, that might already force us to think of what to do with quantum mechanics. And I think this is also related to the second part of your question of mathematical corrections. It's not hard, of course, to just correct quantum mechanics. You add some nonlinear terms. But these terms usually have a big problem. Yeah, for instance, if you looked at Weinberg's nonlinear quantum mechanics, where this happened, the fatal criticism was Gizon and Polchinski. And what Gizon pointed out was that you get superluminal signaling the moment you add these nonlinear terms. And Polchinski had a similar thing where you get communication between branches of the wave function, which really have to do with the fact that these maps have to be completely positive. But the issue is that this also assumes that there is some predefined causal structure where you can talk about superluminal signaling. And if you're in a setup where maybe your causal structure itself is not defined ahead of time and is being defined by what you measure, maybe you can get around some of these constraints. So once again, gravity is important not because everything goes, but because maybe questions like superluminal signaling might themselves depend on what you observe. And so maybe it gives you some more freedom to do some of these things. I'm not saying we have a very good example, but that's the only sense in which gravity might be important. It might tell you some things you take for granted, you might need to revisit.
Okay, thanks. So
Yeah.
do
we have time, or we can keep going on this?
Ask the guy in front. Yeah, 5 minutes.
Okay. A couple of very small comments and a follow-up question for Michael Berry. I think Barbara had alluded to this, that one of the arguments which were being made that, okay, when we actually try to build a quantum computer, we may learn something more about quantum mechanics. Because in the sense that this is probably the first systematic attempt to create a controlled entanglement of a very large number of degrees of freedom. And the generic argument is that once this becomes large enough, it may decohere. So the experimental signatures would be when we are unable to explain the performance of how the quantum computer, is it decohering more than what we understand? Is there some new channel which we are not able to explain? And so far this has not happened, and maybe that will give rise to some new ideas on how to model and bring about changes in quantum mechanics, right? So my follow-up question to Michael is that, I agree with him that there'll probably be a new theory which will explain the current state of the art and improve. But what are the missing elements according to you? There are this thing about gravity is there, and there is this thing about being uncomfortable about macroscopic superpositions. Do you think that these are the two main issues which the new theory will have to address, or is there something else which the new theory needs to address, which is still not very clear?
I don't think macroscopic superposition is one of the main problems. There you have to reckon with the unavoidable interactions with objects outside your system. So, people can argue about that, but I don't think that's fundamental. Gravity is, of course, but the main answer is we actually don't know. Towards the end of the 19th century, before the black body radiation paradox, people didn't know where classical physics would fail, and it was phenomena, observations that led to that, and so it will be again. Gravity is of course a clue. It's very important. There is an incompatibility, as Juan reviewed for us. So that's one of the areas, but there may be others, and we just don't know. The phenomena in classical physics were totally unanticipated.
Thank you, Michael. I'll take the last question, at least from this set. So Sadiq Rangwala has asked a whole page of questions, but I'll just take one of them. As machine learning and its associated offshoots advance relentlessly, what is the expected common problem terrain where AI, ML, and quantum computing machines will compete to solve problems? May I ask Pedram to respond to this? Or anybody else? Barbara?
Well, okay, so maybe a side point, they don't necessarily always compete, but they can also help. AI is used to calibrate devices, do decoding for error correction, tune up quantum dots. Okay, and then there are things that you do like many body problems, strongly correlated systems. People are developing sort of machine learning models with parameters that then can be trained. But I see more as there's a lot of opportunity for synergy actually. And there is this thing, I think, I don't know who alluded to that, there's sort of like, we do something on a quantum computer and say, oh, it's going to take a long time on a classical machine. And then there's another team that says, no, it's not taking a long time because we have a very clever algorithm. So there's this very healthy competition going on right now, what we can do with a quantum computer. But we also believe that at some point the quantum computer will win. But when... Yeah.
When?
We win, yeah. I mean, that you know...
Win-win, I
yeah.
guess.
Right.
Okay.
That's my short answer.
Thank you. I have one last thing to say. Is there any young person, a school student, who would like to ask a question to the panel? There's one school student whom I know very well. So he wants to ask a question. Rupert?
So I'll ask something which actually I kind of was discussing earlier today with someone, and it's kind of connected to, is quantum mechanics the end of the road? Which is you know, you mentioned, oh yeah, of course, black body radiation and so on. You know, that was something which people, you know, that's where classical mechanics failed. And so we may, quantum mechanics is probably not the end of the road. There'll probably be many there'll be theories after theories. But after all, these are just better and better and better approximations. What if we reach a point where these approximations, so what I'm saying is, what if we reach, we are humans, yes, as Sir Michael Berry pointed out, we're just humans, we're of limited intelligence, and therefore, maybe we are also, you know, we are limited by so many things. You know, we can't just keep making accelerators and accelerators until, you know, some new magic results pop up that, oh, this theory is. What if we end up at for fundamental theory of physics, like quantum mechanics or something, a framework of physics rather, if you have something that predicts everything so accurately that, you know, no experiment of yours is going to validate or invalidate it, you know, if that's just too out of, then is physics going to stagnate? You know, is physics going to just end up with a theory that's just very good at predicting things that, and, you know, even the standard model, for example, is surprisingly good, right? It's more accurate than people might think. I'm not saying the standard model will last forever, but yeah, that's my question.
Barbara?
Sorry, I keep saying things. Yeah, I think it's a very good point that our limitations on what we can measure. I mean, but we're also developing artificial intelligence. I mean, I'm sometimes struck that measurements always taking a short. We don't do measurements for, well, we do sometimes experiments, but for tens of years or hundreds of years, right? It's set by our lifetime, which is extremely limiting, right? And so maybe we'd hope that maybe with future higher intelligence, we can take a, you know, it's not only higher energy, it's also maybe longer, looking at phenomena at a longer time scale could give new insights. But I agree, but maybe there are other people have comments on how we can overcome this.
I think often also a lot of the discovery was not completely expected. And then there are many examples, especially that quantum material research is a good example, like the high temperature superconductor is one of the good examples. Certainly, certain class of the superconductor transition temperature is almost order of magnitude larger than what has been seen. I think this is a good example. And many of the very unexpected examples this comes up and require explanation. And some of them we can answer it. Some of them we don't have yet answer. So I don't think that you have to worry about that, oh, we are reaching the end of the road. by just kind of some of this understanding. Nature keep providing us something to think about, something to kind of explain, something to discover. That's kind of belief.
Spenta, can I just?
Yes.
So this is an interesting question in the context of quantum mechanics today. So do we know when we have understood a phenomenon with the existing theoretical framework or not? Because today, when we get an experiment which one set of theory cannot explain, the theorists from another direction will come and say, no, we can actually explain that. So really, high TC superconductivity, which Philip just said, we probably require a time limit. You work for 3 decades, you cannot understand probably means you need a new set of theory. The problem with the complexity and the material understanding and new phenomena that is required, you're absolutely right that with the breakdown of the radiation, the black body radiation led to a strong skepticism towards the classical model. But I think we are not really developing the skepticism enough to say that we need now a different case of theory. So this is where the complexity of the problem has gone to. So maybe we require a different approach here to say that, yeah, that's it. Now we really require something on a new paradigm.
Yeah, I agree with that. In fact, I'd like to say that we have no idea about the experiments that are possible in the next 100 years, actually. I think this is a very important point. So with that, I think we are very much over time. My apologies. And I'd like to conclude this session with a thank you to the panel for agreeing to send so many questions, and to the audience for a very, very lively discussion. Thank you very much, everybody.
And thanks to Spenta for moderating it wonderfully. So thank you again to all the panelists.